On December 28, 2025, Israel took delivery of Iron Beam, a 100-kilowatt class laser built to destroy drones, rockets, and mortars without firing a missile.
3, 2, 1. Target launched. Target engaged. Laser interception in progress. Successfully intercepted.
Target successfully intercepted.
Conventional interceptors can cost at least $50,000. A laser shot mainly consumes electricity, but Iron Beam is not unlimited. It needs clear air, precise tracking, cooling, and several seconds on target. The breakthrough is real, so is the bottleneck. The December handover mattered because this was no longer a laboratory demonstrator or a temporary battlefield prototype. Israel's Ministry of Defense described it as the first complete Iron Beam system, delivered after full configuration tests against drones, rockets, and mortar threats. Additional units were already entering production, but delivery is not the same as nationwide protection. Public information does not reveal how many batteries are operational, where they are deployed, or whether the system can remain continuously ready across Israel. Joint scenarios involving Iron Beam and Iron Dome were still being tested in 2026, suggesting that integration into the wider air defense network remains part of the challenge. Raphael describes Iron Beam as a ground-based, 100-kilowatt class laser with an engagement range extending from several hundred meters to roughly 10 kilometers. Those figures are manufacturer specifications, not independently verified combat performance, and the power number needs context. 100 kilowatts refers to the optical energy leaving the weapon. The generators must produce considerably more electricity to run the laser, sensors, tracking system, and cooling equipment. There's another important distinction. The laser interceptions Israel disclosed from combat in 2025 were carried out by smaller prototype systems, not the final Iron Beam configuration delivered in December. So the key question is no longer whether a laser can destroy a drone. It can. The real question is why using missiles against those drones has become financially dangerous. A defender can destroy every incoming drone and still lose a larger contest. That is the cost trap. A cheap drone or decoy does not need to survive. It only needs to look dangerous enough to force a response. Once a defender launches a missile, that interceptor is gone. It must be manufactured, transported, and replaced before it can be used again. Reuters has reported that conventional interceptors used against these threats can cost at least $50,000 per engagement. The exact figure varies by weapon and target, but the imbalance remains. An attacker can launch large numbers of inexpensive threats while forcing the defender to spend far more stopping them. The real danger is not just the price of one shot. Missile batteries carry a limited number of ready interceptors. During a prolonged attack, the strategic cost is running short before the attacker does. Replacing those missiles may take months or years. Building another simple drone can take far less time. A missile is expensive because every shot contains its own engine, guidance system, sensors, controls, and warhead. A laser reuses the costly hardware and sends energy through the air. But cheap shots do not mean cheap defense. Iron Beam still requires expensive sensors, generators, cooling systems, and infrastructure. Removing the missile from each engagement solves one form of scarcity. It does not remove scarcity itself. A missile battery runs out when its launchers are empty. A laser battery runs out in a different way. Iron Beam can keep firing as long as it has electricity, working optics, enough cooling, and a clear path to the target. That gives it far greater magazine depth than a launcher holding a fixed number of interceptors. But magazine depth is not the same as firing capacity. A laser may have enough energy for hundreds of shots and still be overwhelmed in less than a minute. The reason is dwell time. Light reaches a target almost instantly, but the damage does not. The beam must remain concentrated on one vulnerable point long enough to heat, weaken, or ignite it. If that takes several seconds, the weapon cannot immediately move to the next threat. Those seconds become the real ammunition. A single laser can work through targets quickly, but it normally cannot burn through several separated drones simultaneously. Then there is the atmosphere. Fog, rain, dust, smoke and moisture can absorb or scatter the beam. Turbulent air can distort it. Buildings, terrain, and the curve of the landscape can block it completely. No amount of electrical power can shoot through a hill, so the laser does not remove scarcity. It relocates it. Missiles are limited by the number of interceptors in their launchers. Lasers are limited by power, heat, weather, geometry, and time. And during a concentrated attack, time may be the most dangerous limit of all. Those limits become clearer once the engagement begins. Iron Beam does not simply point at a drone and fire. First, radar or another sensor detects the object. Command software identifies it, predicts its path, and decides whether the laser has a clear shot. The beam director then locks onto a vulnerable part of the target and keeps that exact point centered as the object moves. That tracking is critical. A laser does not need to destroy the entire aircraft. It only needs to damage something the aircraft cannot function without. Against a drone, that could be a wing, control surface, motor, battery, sensor, or fuel system. The result may not look dramatic. The target might not explode. It may simply lose lift, lose control, or suffer enough structural damage to fall from the sky. To produce that effect, Iron Beam combines energy from multiple laser modules into one concentrated beam. Raphael says adaptive optics help correct distortion caused by turbulent air, while an electro-optical targeting system keeps the energy focused on the chosen aim point. Those are manufacturer descriptions, and public evidence does not reveal how well the system performs in every real-world condition. The advertised 100 kilowatts also tells only part of the story. That figure refers to the optical power leaving the weapon, not the electricity required to run the complete system. Lasers are not perfectly efficient. Sensors, computers, tracking equipment, pumps, and cooling hardware all consume additional power. Consider a simple illustration. If a 100 kilowatt laser operated at 40% electrical efficiency, it would need roughly 250 kilowatts of input power. About 150 kilowatts would emerge as waste heat before the supporting equipment was included. That heat must be removed. If components become too hot, performance in decline or firing may have to pause. Repeated engagements therefore depend on chillers, coolant circulation, outside temperature, and how long the system can operate before cooling becomes a limiting factor. The beam can even interfere with itself. As intense energy heats the air along its path, the air can begin to distort and defocus the beam, an effect known as thermal blooming. Adaptive optics can compensate for some turbulence. They cannot make fog, smoke, or a building transparent. That is what makes Iron Beam more than a powerful light source. Its real engineering achievement is coordinating detection, tracking, beam control, electricity, and heat removal quickly enough to turn energy into a reliable weapon. Iron Beam's precision is also what makes it vulnerable. The beam concentrates energy on one exact point, reducing wasted power and limiting damage around the target. But it usually means one beam director attacks one object at a time. Rapid tracking helps. It does not change the sequence. A drone must be detected, assigned, tracked, heated, and confirmed as defeated before the beam moves on. If several threats arrive within the same few seconds, the laser can have plenty of electricity and still fall behind. An attacker does not need to defeat the beam itself. It can try to consume the weapon's available engagement time. Drones can approach from several directions, hide behind terrain, mix with decoys, or compress their arrival into a single wave. Each tactic forces the defense to divide attention and decide which targets must be stopped first. That is why some militaries are testing a different kind of directed energy weapon. A laser heats one precise physical point. A high-power microwave system spreads electromagnetic energy across a wider area, attempting to disrupt or damage the electronics inside several drones at once. In 2023, the U.S. Air Force Research Laboratory says Thor demonstrator disabled a simulated drone swarm using a broad electromagnetic effect. The U.S. Army later tested another high-power microwave system during exercise Balacatin in the Philippines in 2025. The appeal is obvious. One pulse could affect several aircraft. But microwaves introduce different uncertainties. Their effectiveness depends on how vulnerable the target's electronics are. Shielding and hardening can reduce the effect. A broad pulse may also threaten nearby friendly equipment, while operators may struggle to confirm whether a drone has been permanently disabled. Lasers offer precision. Microwaves offer potential area effect. Neither solves every part of the swarm problem, The stronger answer may be a layered mix of lasers, microwaves, guns, interceptor drones, and missiles. With each weapon assigned to the target it can defeat most efficiently. That layered approach sounds logical. The harder part is fitting each weapon onto a platform that can support it. The U.S. Army learned this with DEM SHORAD, a 50-kilowatt class laser mounted on a Stryker armored vehicle. The weapon drew energy from batteries, while onboard diesel generators recharged them. Its magazine was therefore fuel, battery charge, cooling capacity, and the time required between firing cycles. The Army deployed prototypes overseas for assessment, but the system was judged insufficiently mature to transition as planned. By July 2025, the Army was no longer pursuing that configuration as a program of record, and several prototypes had been demilitarized. The laser physics had not failed. The platform had exposed the trade-off. Every armored vehicle has limited space, weight capacity, electrical generation, and heat rejection. Increasing laser power can demand larger batteries, generators, chillers, and optical equipment. But the vehicle must still move, survive, carry a crew, and remain maintainable in the field. Ships and fixed installations operate under different limits. They generally have more room for generators, cooling equipment, and maintenance access. That helps explain why the U.S. Navy reported successful testing of the Helios laser aboard USS Preble in autumn 2025, while high-power microwave systems continued moving into Army counter-swarm trials. The lesson is not that one country has mastered directed energy and another has not. A weapon can succeed in a demonstration and still fail as a deployable system if its platform cannot sustain it. Israel may benefit from matching Iron Beam to a narrower mission. Short-range offense from prepared positions, connected to mature sensors, and an existing layered network. Even then, the economics will not remain one-sided. Once defenders change the cost of interception, attackers begin searching for ways to raise it again. That response will not make Iron Beam irrelevant. It will determine how much pressure the laser can absorb. Its clearest advantage is economic. Every drone destroyed by electricity preserves a missile for a target the laser cannot reach, see, or defeat quickly enough. The same optical hardware can engage repeatedly without launching another explosive interceptor. But the laser remains one layer, not a replacement for Iron Dome, David's sling, or arrow. It needs direct optical access. Rain, fog, smoke, dust, and turbulence can reduce the beam's concentration or shorten its useful range. One beam normally services one target at a time. Generators and cooling systems create maintenance demands and signatures. Even a successful interception may leave fragments falling below. Several measures remain undisclosed, including sustained firing rate, dwell time, degraded weather performance, independent probability of kill, and full lifecycle cost. That leaves attackers several responses. They can compress arrival times, approach from multiple directions, use terrain or obscurance, protect vulnerable components, or attack the laser sensors, power supply, and cooling equipment. None is publicly proven to defeat Iron Beam. The goal is to force the system into conditions where another weapon must take over. This is where battle management becomes decisive. Software can compare the target, trajectory, range, weather, and available weapons, then assign the cheapest effector likely to succeed. A visible drone may go to the laser. A dense electronic swarm may go to a microwave weapon. A nearby target may be handled by a gun or interceptor drone. A difficult targeting cloud or beyond laser range still demands a missile. The contest is no longer about one weapon. It is about how efficiently the network spends its seconds, energy, and ammunition. Iron Beam does not end the drone threat. It does not replace missiles, and can still be overwhelmed by weather, terrain, or too many targets arriving at once. What it changes is the cost of staying in the fight. Some threats that once consumed a scarce interceptor can now be defeated with electricity, cooling capacity, and a few seconds of beam time. That preserves missiles for targets the laser cannot handle. The magazine has not become unlimited. It has moved from launcher tubes into generators, cooling systems, clear lines of sight, and decision time. Iron Beam's real purpose is not to make drones obsolete. It is to stop cheap drones from deciding how an entire air defense network spends its ammunition.